Okay, in this lecture we're going to look at transition probabilities, joint probabilities, Markov chains, what else? Fokker-Planck equation, and maybe a few other things. Okay, in particular detailed balance. So, let's introduce transition probabilities. So if you have a stochastic process like a Brownian walk, we can describe it in terms of transition probabilities, which tell us the probability of an event occurring at a particular time where conditions are specified at another time. Okay, and as usual, we're going to let K here stand for this, the pair, XK, TK. So P12 is the probability density of finding 2 when 1 is given. That's the definition of P12. P1, 2, 3 is the probability density of finding 3 when 1 and 2 are given, etc., etc., P1, 2, 3, 4. Okay? And probability density here means the probability in an X interval of the variable X1, X2, or X3 in these particular cases. Okay, so P1 bar 2 is the important thing to focus on, the probability of finding 2 when you're given 1. Now, of course, we can express joint probabilities in terms of transition probabilities. So here we go. These are transition probabilities there. So if we want this joint probability, the probability of 1 and 2 occurring, if you think about it for 2 seconds, that has to be the same thing as the probability of 2 occurring given that 1 is occurring, times the probability that 1 has occurred. Okay? And similarly, if you have you want the joint probability of 1 and 2 and 3 happening, then that's the probability of 1 and 2 happening times the probability that if 1 and 2 are happening, 3 is happening. Okay, and similarly for longer and longer and longer chains. Okay, so the properties that these probabilities must satisfy are obviously that the probability of 2 occurring if 1 has occurred must be bigger than 0, and the integral over all possibilities 2 must be 1. Okay, this is normalization and positivity. Since W12, the probability of 2 occurring, must equal the integral over all possible 1s of W212, we also must have this. Okay, because that can be expressed that way. Okay, and that gives us an integral equation for W1. We won't use any of this stuff. Okay, now we come on to a very meaty and very helpful law of, well, it's a mathematical law, it's just common sense really, but detailed balance is very, very useful in physics. It gives you information which you almost from nowhere, and in systems which are in steady state and equilibrium. You have an equilibrium kind of system. So what is detailed balance? Okay, well, for the point probabilities, we have from symmetry W212 equals W221. Okay, basically this is the probability of 1 and 2 happening, and this is the probability of 2 and 1 happening, and of course those two probabilities must be the same. Okay, so it's W12 is the probability that X is X1 at time T1 and it's X2 at time T2, and that's obviously the same as W21. Okay, so that's very true. This is obviously true. However, it's certainly not true for the transition probability. So this joint probability is okay. This transition probability is certainly not true. It's certainly not true that the probability of 2 occurring given that 1 has occurred is normally equal to the probability of 1 occurring given that 2 has occurred. They are not equal in general. However, we do know the fact which we just described, which is that W12 is equal to W1 times P 1/2. Okay, and that W212 is equal to W21. And so that gives us the following equation, which certainly is valid, which is that W1 times P12 equals W2 P21. Okay, and that's called detailed balance. And it's basically, in words, it says at equilibrium, each elementary process should be equilibrated by its reverse process. Okay, the rates, the forward process and the reverse process must occur equally to be in equilibrium, otherwise you'd be still evolving in time. Okay, so let's give an example of that. We'll give some examples outside of physics because they make things a lot clearer, I think, and it's often they're more interesting. So let's give the example here of Anais Nin, She's a literary figure from the mid 20th century. Her diaries are often read these days. Her actual literary work is not so well read. At least it's well read, but not in universities because it's a bit spicy, and the politically correct mafia might try and censor it. So you won't find her work studied heavily in university courses. This is an example here of a dynamical system with rates. Okay, so we're going to use her life. And she was a very bohemian person, and so bohemian, in fact, that she had two husbands simultaneously, one in New York and one in Los Angeles. She didn't divorce the first one and marry the second one. She married them both. Okay, and that's normally called bigamy, and it's illegal, at least for the moment, in most places. So let P NY be the probability that Nin is in New York with her New York husband, and similarly PLA, which is the probability that she's in Los Angeles with her Los Angeles husband. Okay, and let us say that P NY/LA is the probability unit time that she will leave for LA, given that she's in New York. So there's a certain probability that she's in New York, that she will that day go to LA. Okay. And similarly, there's a certain probability if she's in LA that she will go to New York. There's a certain rate of that. So what does detailed balance tell us about this? Well, detailed balance tells us that this probability must be true, this probability equation. The probability that she's in New York, and the probability that she's in LA, and the rate from going to New York to LA, and the rate from going from LA to New York must obey that equation there. Okay, assuming she can only be in Los Angeles or New York. Okay, that's the assumption there. All right, she doesn't stop on the way. All right, so here's New York, here's Los Angeles. We're assuming that Anais Nin travels instantaneously between these two to visit her various husbands. Okay, so we know. Let's assume we know the following rates. That the rate of leaving New York and going to Los Angeles, if she's in New York, is 0.05 per day. And if she's in Los Angeles, the rate of going to New York is 0.1 per day. So that typically if she's in New York, she will wait 20 days before decamping to Los Angeles, and she camps to Los Angeles at twice this rate. Okay. We want to know the question is, what fraction of her time F is spent with her New York husband? Okay. So we've got F equals probability of being in New York. The probability of being in LA must be 1 minus F. We're assuming she has no more husbands. She only has two, and she doesn't have one somewhere else or several others in Florida or somewhere. So we're assuming she only has this, so two husbands. So probability of being in LA must be 1 minus the probability of being in New York. So there. Okay, so what does detailed balance? Detailed balance tells us the equation which we saw before, and that means that F, which is this thing here we don't know about, there's 1 minus F, which is from there, and we have the rates here, 0.05 and 0.1, and you can then solve that equation there, and when you solve it, you get F equals 2/3. So she spends 2/3 of her time with her New York husband. Okay, that's the plan. Her scheme of having two husbands caused her, of course, immense problems, and she had a special secretary who was basically in charge of making sure all the lies she had to make up made some kind of sense. Eventually, this scheme of hers unravelled when both husbands claimed her as a dependent on their tax returns. And the Internal Revenue Service said, hey, what's going on here? And they looked into things eventually, and of course, she was married to two people at once. Okay. Right, so a more normal use of detailed balance, not to detect bigamists, but in science, is in chemical reactions in solution or in gases. So you might have a beaker with some molecules of different kinds. Here's two kinds of molecules, and they could be in gas as well, like that. Okay, so we've got something like nitrogen plus oxygen goes to some other stuff plus some other stuff. It's a typical chemical reaction. Okay, and it's an equilibrium. Here we've got this little reversible reaction occurring there. Okay, so what are we going to do here? In order for this reaction here to proceed, this one, we need A to meet a B. If A doesn't meet B, we can't get a reaction. Not only does A need to meet B, so here's A and here's B, they need to meet, but when A meets B, there will also be a barrier. So normally if A has met B, it doesn't mean the reaction will proceed, but if A has met B, then you've got maybe the reaction will proceed. Okay, so the fact that A has to meet B for the reaction to go ahead means the probability of the one state, we'll call this side the one state if you like, the two state, okay, is proportional to the concentration of A times that of B. So, if A has to meet B, you want to know the probability of them meeting. Well, it's going to be proportional to the concentration of A and the concentration of B, okay, assuming everything's just randomly colliding. And similarly, for the two state to happen, you must have probability must be proportional to the concentration of C and the concentration of D. Sort of random kind of collisions occurring. Okay, so that's what P1 and P2 are at least proportional to. Okay, now once A and B have met, there's a certain rate for the forward reaction to occur, and that rate is K plus. The reaction A plus B goes to C plus D. That has a rate K plus. Okay. And the reverse reaction, if you've actually got some C and D already meeting, C plus D goes to A plus B, that has a reaction rate K minus. So there's the reaction rates. Okay, and so detailed balance will just tell us very simply, assuming the proportionality constants here are the same, which they will be, that K plus times the concentration of A times B equals K minus times the concentration of C times D. Okay, there's our rates, there's our initial probabilities of being in each state. And that's what detailed balance tells us. And in chemistry, this ratio here, concentration of C times the concentration of D divided by concentration of A times the concentration of B, these brackets mean concentration, is called the equilibrium constant. And detailed balance tells us the equilibrium constant is the ratio of the two rates, Kf and K forward and K reverse. Okay, so that's an application to chemistry. Okay, now of course chemical reactions can occur in many different ways. They're not all A plus B equals C plus D. Sometimes you have to get two A's and three B's together, and they form maybe some different numbers of C's, maybe 5 C's and 2 D's. Okay, so sometimes there are prefactors here, which means that suppose A was 2 and B was 2, then 2 A's would have to meet 2 B's for the reaction to occur. Okay, and therefore in those cases the probability, maybe this should be proportionality, the probability should be proportional to A to the alpha, B to the beta, if I have alpha A's and beta B's meeting. And similarly for all the rest of it, and detailed balance will then tell you get the following equation, okay, because you have to have gamma C's and delta D's meeting to do the reverse reaction, okay. The equilibrium constant in that case is given by this, and detailed balance, that's detailed balance. The equilibrium constant is defined by that, and detailed balance again tells us how the equilibrium constant is related to the forward and reverse reaction rates, and it's the same as before. Okay, enough of chemistry. Let's move on to something that looks a bit more like physics. Let's look at an ionized plasma. So if you heat hydrogen gas up high enough temperature, you get the hydrogen molecules breaking up into H and H. And if you heat it up even more, you find that the H itself breaks up into a proton, H plus, a proton, plus an electron. Okay, completely ionized. The electrons are removed, so you have basically a gas consisting of protons and electrons, but maybe at the same time in equilibrium you have some hydrogen. So in equilibrium you have these things floating around all together, they constantly exchanging. Okay, so this obviously has obvious applications to astrophysical systems and also to fusion energy research, which has been going on since about the end of the Second World War, and continually promising us, basically very clean, very free energy, and it hasn't worked yet, but it's been a great employer of physicists. Okay, so NH is the density of hydrogen atoms, and N plus is the density of ionized hydrogen, in other words protons, and Ne is the density of electrons. So we've got three densities here. Okay. On the left-hand side of this equation here, the one probability is simply proportional to NH, because here, it's proportional to the density of hydrogen. Here we don't have to have hydrogens meeting. Okay, they just one hydrogen just disintegrates itself. Okay, so you don't have two hydrogens meeting, so therefore P1 is simply proportional to the concentration of hydrogen. On the right-hand side, in order for this reaction to reverse, you must have a proton meeting an electron, and therefore the right-hand side reaction rate is proportional to N plus times Ne. The ionization rate Ki and has a rate Ki, and the recombination rate has a rate Kr, which we don't know. Okay, so this has a rate Ki, this one is K recombination, which is Kr, and we don't know those at the moment. Okay, so here's our equation again. Detailed balance tells us this: NH times Ki must equal N plus times Ne times Kr. We know that's different from the equation we got from chemistry, from the chemical reaction, because we only have one species here on the left. Okay. Now, we can obtain this ratio, N plus Ne on NH, using thermal equilibrium, basically using an equation called the Saha equation, which is based on a combination of quantum mechanics and Boltzmann distribution. We won't write it down, but if you looked at it, you'll find it's very familiar to you from this course. This was invented by Meghnad Saha, an Indian physicist invented in 1920. And Saha was one of the great Indian physicists from the time before India gained independence. We also had Bose, and we also had Raman, for instance. After they gained independence, we don't find too many people of that caliber coming through physics, presumably they were doing other things. Okay, so anyway, from this we get the reaction rates, and so therefore you can use detailed balance. If you know, for instance, one of these, you can figure out what that one is. Okay, now to figure out both of them at the same time, to figure out one of these, you need some kinetic theory to do that. So we're not going to do that, but detailed balance gives us a lot of information about the overall reaction rates. Okay, let's move on to a different topic here, which is Markov processes, which you might have met before somewhere in maths. Okay, so before doing Markov processes, we'll do something even simpler. There are things that are purely random processes with no correlation. So if we flip a coin or roll a dice, there should be no correlations between successive events. So if you flip a head, the probability you're going to get a tail, it doesn't depend upon the fact you flipped a head. Okay, similarly, if you roll a 6, the probability you're going to get a 3 next time has no influence whether you rolled a 6 or whether you rolled a 2 beforehand. That's the idea anyway. So for purely random processes, the probability of 1 and 2 occurring is the probability of 1 times the probability of 2. Okay? And 1, 2, 3 is the probability of 1 times the probability of 2 times the probability of 3. So these are all processes where there's no correlations and everything's completely independent of each other. And these systems have very severe dementia. They remember nothing. They don't remember what happened in the past. They don't care. Okay? As Huang points out in his textbook, it's difficult for a continuous physical system to be totally uncorrelated, as x of t plus delta t must depend to some extent on x of t. Okay, if delta t is small enough. I mean, having things completely uncorrelated is really, really hard. But we do hope that dices and coins and things like that, dice and coins are this way. Okay, these are completely uncorrelated, completely random between successive events. Okay, so that's the simplest kind. Okay, those kinds you already know how to do. So next in complexity are Markov processes. These were studied by Andrei Markov in 1906. It's a Russian mathematician. In these processes, there is bad dementia, but not absolutely appalling, because they can remember what just happened, and only what just happened, at the last step, but nothing else in the past. Okay? So, in other words, the probability of state n happening, given the probability that states 1, 2, 3, 4, 5, 6, 7, 8, n minus 1 has happened, is the same as the probability that state n minus 1 has happened. Okay? Alright, so all these guys here don't do anything, and only the state just prior to the one you're interested in is what matters. And here we've got Tn is bigger than Tn minus 1, Tn. Okay? So for these, if we know the probability of 2 happening given 1 happens, then we know everything. Okay, so the probability of 1 and 2 and 3 happening is the probability of 1 and 2 happening times the probability of 3 happening if 1 and 2 is happening, and that's the same thing as this times that, because this is the same. Probability 1 and 2, probability of 3 happening given that 1 and 2 has happened is the same thing as the probability of 3 happening given that 2 has happened. And then you can expand this out again to that degree if you wanted to. Okay, so it forms a chain. We go from 1 to 2, well, 1 to 2, 2 to 3, etc. Okay, so these processes are, the n step depends only on the n minus 1 step. Okay, so Markov. Here's this little anecdote about Markov. There he is. Before the Russian Revolution, there was a lot of, shall we say, seething discontent. And so, the Russian Revolution happened in 1917, but there were a lot of, from the 1880s, 1890s onwards, there was a lot of discontent. And of course, a lot of that discontent occurred among students. So professors and lecturers at St. Petersburg University, where Markov was, were ordered to monitor their students for political things, political activities. And Markov refused to accept this, and he said, look, I'm not going to be an agent of the governance. I'm not going to spy on students. So basically he was removed from his teaching duties, and he decided to retire from the university. Markov was also an atheist, and in 1912 the Russian author Leo Tolstoy was excommunicated from the Russian Orthodox Church by requesting his own excommunication. I think he had his own views on religion, no, maybe the church excommunicated him anyway. But then Markov decided he wanted to be excommunicated as well, and he asked the church to excommunicate him, and they said, yes, of course we will. Okay, so they got rid of him. All right, so where do we find these Markov processes? Brownian motion is a natural one where there's hardly any correlations. Where you go depends only on where you were the last step. Quantum mechanics and Fermi's golden rule. Some really primitive car cruise control. Basically your future, the future decision of the car only depends upon its current speed. That would be true in very old cruise controls. I have a feeling modern cruise controls start looking back in time a lot more. If you have a board game based entirely on dice, like Snakes and Ladders, that's a Markov process, but not card games. Okay, normally they have memory. So when Sylvia Trench and James Bond are playing blackjack, whatever they're playing, they need more than just Markov. Okay, you have to analyse the previous cards as well. Okay, so let's do a couple of examples of Markov chains. We'll do one, given that Markov was Russian, we'll do one about Napoleon invading Russia. Okay, so here's Napoleon at the burning of Moscow. The Russians themselves have set Moscow alight. And so Napoleon, of course, conquered a great deal of Europe and made it into Egypt. However, he made a monumental mistake in invading Russia. And when people invade Russia, whether it's Napoleon or Hitler, what happens is the Russians just retreat further and further into their country, and they burn everything. Okay, the scorched earth policy, so that the invading army has no possibility of supplies from the land. Okay, this is particularly true and particularly important for Napoleon. Okay, warfare in those days, you had to get food from somewhere. What happened? This is what happened to Napoleon, and after waiting pointlessly around in Russia, Napoleon had to return to France, defeated by the horrible Russian winter and also lack of supplies. The Russians just destroyed everything. Okay, of the 600,000 troops he took with him, he only returned 100,000 back to France. So a lot of widows were made by this crazy campaign, and then the Russians started to follow him westward towards France, which was a bit worrying, of course. So let's assume Napoleon can be in 3 locations only: France, Egypt, and Russia, and you can swap between those three as much as you like. So France, Egypt, Russia, and we had to invent some probabilities. Okay, so if he's in France, the probability his next step will be Russia is 0.6. If he's in France, the probability his next step will be to remain in France is 0.1. And if he's in France, the probability he'll go to Egypt is 0.3. And similarly, if he's in Russia, the probability he stays in Russia is 0.9, because he was trapped there for a long time. The probability he's in Russia that he goes back to France is 0.1. The probability he goes from Russia to Egypt is 0. Okay, so we have all these different probabilities. And we're going to represent Napoleon's current state by a matrix, which looks like this. And so he's definitely in France, then we get a column vector looking like that. That says Napoleon's in France and he's not in Egypt or Russia. Okay, so we also draw a picture like this. You can draw a picture like this. This is France, and this is Egypt, and this is Russia. and you can draw a little diagram that shows all these probabilities. So the probabilities in France and stays in France during that step is 0.1. So you draw a thing like that with 0.1 on it. The probabilities in France and the next step goes to Egypt is 0.3. And the probabilities in France and the next step he goes to Russia is, where is it? Where is France to Russia? Where is France to Russia? Oh, 0.6. Has to be that. They'll add up to 1. And similarly, I'm not going to fill out the whole diagram, but so for instance, the probabilities in Russia and goes to Egypt is here, and that's 0. So this one is 0. And the probabilities in Egypt and goes to Russia, for example, is another arrow going like this, and that's Egypt to Russia is, where is it? 0.1. Okay, so there's a few more arrows on that diagram you need to fill in, but you can also draw a diagram like that, which often helps you. Okay, so transitions between states are represented by a square matrix like this one here. Okay, and if you look at the first row, it's just the probability of going from France to France, probability going from Egypt to France, and the probability going from Russia to France. Okay, and then similarly, the second row is the probability going from France to Egypt, from Egypt to Egypt, and from Russia to Egypt, etc., etc., etc. And if you want to figure out what's happening, you have to multiply this by the column vector, which we'll do in a minute. And if you look at each of these columns here, they all add up to 1. That column adds up to 1, that column adds up, and you might want to think about why that has to be. Okay, it's pretty easy to figure that out. All right, so to get Napoleon state, after one step, we just multiply the column state vector by the transition matrix. So here's one step. So we're assuming he starts in Paris or France with probability 1. Now these probabilities, this state vector doesn't have to be integers. It doesn't have to be 1. It could be, it could be 0.2, 0.3, etc., etc., etc. But we're going to say he starts guaranteed to start in France. Okay. So after one step, we just multiply these two things out. So we do 0.1 times 1 plus 0.8 times that plus 0.1 times 0, and we get 0.1. And similarly, we do that times that, we get 0.3, and that times that, which you get 0.6. Okay, and so this, after one step, is the probability is in France, in Egypt, or in Russia. Okay, and so he's got a probability of 0.6. He's in Russia, basically. Okay. Now, where will he be after n steps? Well, after n steps, what you have to do is you have to multiply this matrix n times. Okay? And in general, these kind of problems, you need to know how to raise matrices to powers. Now, we won't ask you to do this in this course, but I'll put up a video showing you how to do that if you want to know how to do that and you don't know already. But basically, in order to do that, in general, you have to solve the eigenvalues and eigenvectors of this matrix. Okay? In the limit of large n, the final state you get is proportional to the eigenvector of that matrix, which has the largest eigenvalue. Okay, so we'll see that in a minute. We won't actually do it, but we'll see what happens for large n. So after two steps, if you do it manually, or when I say manually, I mean using Mathematica, multiply the two matrices together, square it, and after two steps you're there. Okay, you can see he's got not so much chance of being in France, very little chance of being in Egypt. And after 5 steps, he's got a very high chance of being in Russia, and not much chance of being in Egypt, and a very little chance of being in France either. Okay. After 20 cycles of this thing, it's actually barely changed. So you see this is 0.807, this is 0.13. We've gone to 0.13 and 0.82 here. So after 20 steps, we're almost asymptoted. And in fact, the long-term result here is that I think this is not. Let's see, where are we? I see long-term result. This is probably actually after 5 steps. This is 5 steps was what happened. I think. No, after 5 steps we already know. So I don't know what's going on here. Okay, sorry. This is after 20 steps. After 20 steps, it's basically asymptoted. So after 20 steps, we're getting to here. This is where he's at, okay? And if we did it for 40 steps, it wouldn't change very much, okay? The long-term result does not depend in general on where he starts, okay? So let's him start in Egypt. Here's if he starts in Egypt, make a 1 there rather than there, and the long-term result you get after applying this matrix many, many times is still, it should be 20, I think, is still what we got before. Okay, so after 20 steps, you're still where we are before. Okay, so in the long term, Napoleon spends most of his time in Russia, which is fair enough because we've already told you that if he's in Russia, he tends to stay. Where are we? Back here. The probability of in Russia to stay in Russia is 0.9, so he's basically trapped there. And long term, on average, he's going to be spending an awful lot of time in Russia, not much time in France, and almost no time in Egypt. Okay, so that's what happens long term. Okay, and I should point out in general, this is true. It doesn't matter where you start, except of course for completely pathological cases where you had, for instance, France, Russia connected by some things like this, but Egypt was not connected to anything else. And of course, if you start in Egypt, then of course you have to stay in Egypt. Yeah. And if you start in Russia, you never get to Egypt. So you have pathological cases where the result does depend on your initial conditions, but they're quite rare and very obvious, very easy to spot. Okay, so let's go back to Anais Nin and let's treat her as a Markov chain. Okay, so this is a problem for you to do. So we're going to set up Anais Nin's problem of the two husbands with a vector looking like this. You've got a vector, this is in New York or Los Angeles. And from the rate data given previously, and assuming one step is 1 day, that's what we're going to make one step is 1 day, you should be able to figure out the transition matrix looks like this for this particular problem. Go away and do it yourself, make sure you can derive that. And after many days, you should get a state vector, this thing here, which looks like what you know from detailed balance. In other words, it should look something like 2/3, 1/3. Okay, that's what you should get for your answer if you propagate this Markov chain, say 20 times or something of that order. You'll get something looking like this. Okay, or if you do it by the exact eigenvalue method, you'll be able to prove it looks like that. Okay, so that's a problem for you to do. Right, so we're going to finish this lecture by looking at continuum equations for the probability density P of x of t. And these are very, very useful in a whole lot of areas, particularly in transport processes and semiconductors and in plasmas and a whole lot of applications of these things. These have many people's names associated with them: Smolchowski, Kolmogorov, and Fokker and Planck. And here's Mr. Fokker, who's Adrian Fokker, who's a Dutchman. And he's also famous as a musician. He invented a particular special kind of organ. Originally, he supposedly started working on music theory because the Nazis had invaded Holland during the Second World War, and he wanted to make sure that the Nazis didn't think he could do anything even remotely useful, so he started working on music. And that's the story, at least. Okay, so just a bit of an aside. We have to have P of 2 given 1 satisfy the following equation because it cannot be arbitrary. It must, P of 1 given 3, for instance, must satisfy P of 1 given 2 times P of 2 given 3. Right? So that must be true. And we might use that later on. So what about the Fokker-Planck equation? It's a differential equation describing the time and space evolution of the probability distribution for Markov processes. And we've seen versions of this when we looked, for instance, at diffusion equation. Okay, so and we're assuming infinitesimal jumps for each. It's a sort of continuous Markov process, infinitesimal jumps. An example is diffusion of a random particle. That's the simplest kind of Fokker-Planck equation. So as I said, it's also named after Kolmogorov, a Russian mathematician or physicist who derived it independently, a little bit after Fokker and Planck, and the Smolchowski equation as well. As I think he's Polish, I'm not sure. We're not going to derive this equation. If you want to derive it, go and look at the textbook for one, and I've also put a video up which you can see someone else deriving it. So the result for the probability distribution of P of x of t, this should be really x of t, is this. The P to t plus a first derivative term in x plus a second derivative term in x times something, some things times the probability. Okay, AX and BX depend on the sort of type of Markov process you have. So in general, you can't say what they are until you tell us what the Markov process actually is you're trying to model. Okay, but we can get A and B as follows. So we update one Markov step from x to x plus dx in a small time dt. Okay, suppose we have a Brownian particle. This is our position. It changes by dx in small time dt. the average change is given by this, okay, which is the integral over dx of dx times the probability of undergoing that jump dx, and the average change of the dx squared is simply just put a dx squared there, okay. And the assumption, which turns out to be true, is that both of these are ordered dt, so we can say A is that limit and B is that limit, okay. And when you've done that, we can then figure out what these things are in the Fokker-Planck equation. Okay, so let's do the very simplest example, or maybe not the simplest, but very close to the simplest. We're going to do free diffusion of a particle in 1D. So we're going to do a random walk in 1D. It probably goes doing this, you're backwards and forward, okay, all the time. Okay, we know that the average step in the x direction is 0 because it's free diffusion. It's forward and backwards is 0, and we know in time dt. So that means that time dt does not step more to the left or to the right. And also, of course, we also know in one dimension this result for the average change in x squared. It's 2 times the diffusion constant times dt. You divide both these things by dt, and we get a equals 0, b equals 2d, and the Fokker-Planck equation, which is this, just becomes our diffusion equation, which is very nice. Okay, so again, we're showing that random walk is the same as diffusion, the sort of thing that Einstein had already discovered a long time ago, 100 years ago, more than 100 years ago. Okay, so the Fokker-Planck equation reduces to the diffusion equation with a diffusion constant there, which we know about. Okay, let's do another one. Okay, so we're going to do it. This is possibly even simpler. We're going to do a 1D deterministic particle moving at constant speed v. Okay, so this is going to give us the probability distribution for that kind of particle. It starts here and it just goes like this. Okay, and how does the probability distribution change? Okay, so you might have a probability distribution starting like this, and of course we know what's going to happen to it. This thing's just going to move as a pulse straight through the system. Okay, as it goes further and further along. Okay, so oops, I don't want that at all. I want this. Yeah. Okay, so let's do that. We know that dx, and the average value of x is just v dt. That's what the particle's doing. It's moving at constant speed v, and we know that dx squared is v squared to t squared. If we divide that through by dt here, we get a is equal to v, and b is equal to dx squared divided by dt, which is 0. There's no diffusion in this problem, so that's sort of b is the diffusion-like thing, and you find it's equal to 0, of course. So when that happens, the Fokker-Planck equation here gets reduced to this because the diffusion term goes away, and the constant here, a, is a constant which is this v, and of course that has solution which is just a propagating pulse. Looks like that. Okay, the whole probability distribution propagates the rate at speed v. So the Fokker-Planck equation in that case also makes a hell of a lot of sense. Okay, it's going to give you sensible results. Now we'll finish off by doing one more, slightly more sophisticated example, which is quite puzzling. So let's have a look at it. So we've got a 1D probabilistic particle moving at a speed which is taken from a distribution, PV. So we've got a 1D particle, but its speed can be anything taken from this distribution. P of v is the probability that speed is between v and v plus delta v. Now, if you figure out what's going on there, you'll find that dx is equal to v dt, where v is the average of v, so v here is equal to v p of v dv. Okay, and dx squared is proportional to t squared because there's no real diffusion here as far as things go. So therefore, we're going to get that v, a is equal to v, the average v, and b is equal to 0. And we end up with this equation, which is here. Okay, the whole probability distribution propagates the right at a speed v. So remember, we've got this guy here. His speed, he can choose it randomly. Okay, his speed is chosen randomly at each point. It's chosen completely randomly, so you might do that, and you might do this, and you might do that, etc., etc., etc. You might even go backwards. And what we've found is that this is the equation the Fokker-Planck equation becomes, and the probability distribution propagates the right at a speed which really has no randomness in it. So there's no randomness here in this thing. Okay, well, there's randomness here, but it doesn't appear in the end result. It's just a pulse which propagates at the average speed from the distribution. Okay, so it doesn't have any spread. I mean, you might ask why the hell it doesn't have any spread, because I'd expect a spreading out of the particles, because if we take a very simple example, a velocity distribution which has just two speeds, v and 2v, each of them equally probable, if we start with a delta function distribution at time t equals 0 and x, so we've got a delta function here, in each time step, delta t, the particle can choose with equal probability to move with speed, to move a distance v delta t or 2v delta t. And surely we expect this thing to spread out. We should expect it to spread out more and more and more. Okay, but the FokkerPlanck equation tells us it remains as a delta function and moves at this speed, the average of the two. Okay, and the reason why this happens against all everything you'd expect is because this is a continuum process, this FokkerPlanck equation. So this means, suppose we have a system we want to calculate the probability that we have chosen p steps of size v delta t and n minus p steps of size 2v delta t after n time steps. So we're going to do a discrete version, and we're going to have n time steps of size delta t, and we're going to say, well, what's the probability of choosing p of them that have size v and n minus p of them that has size 2v? Okay, let's try and do that. Well, that's n choose p, half the n minus p, assuming they're equally probable, and I get this result here. Okay, which is I've reproduced here. Okay, now this means there's a finite probability of choosing all kinds of distances. We have all these different kinds of distances in principle. Okay, so we expect a spread. However, in a limit of large numbers of time steps, n, this function is strongly peaked about p equals n on 2, and all the other scenarios give zero contribution. Okay, now the thing is, we have a continuum distribution, so we have an infinite number of time steps. Okay, so all the other bits of this, which are not about n on 2, p equals n on 2, contribute nothing. Okay, and so it's the average speed that matters, and our answer is the correct one. But if we had a really truly discrete system, this would not be true. So that's a rather confusing example, but it's one that shows you have to be a little bit careful when using the FokkerPlanck equation, particularly if you're doing it numerically. You might end up with results which you have trouble interpreting. But in general, the FokkerPlanck equation is very, very useful in calculating probability densities as a function of x and time, or in other words, number densities. If you have a plasma and you want to know, what's the number density of electrons here and this field configuration, you can use a FokkerPlanck equation to see what goes on. Okay, and that's the end of the lecture.